topic will be about line balance improvement with global optimization. John Behnke, General Manager FPS from Inficon, will give us an overview of the challenges and drivers of line non-linearity and the use of I4.0 solutions that leverage a digital twins learning comprehensive dataset. John, please.
Thanks. All right, well, thank you very much. It's kind of hard to follow Microsoft. That's kind of a tough order, sorry. And I'm speaking to you about, what time is it here? 2:30 in the morning from Austin, Texas. So good afternoon. I'll try to stay awake, just kidding. But thank you very much to SSIA for inviting me to talk again. And I'm very excited about talking about, I guess, a topic that's a little more tactical than what we have been hearing from the previous speakers. I'm going to speak to you today about really the efforts associated with getting more out of an existing factory through improving linearity. If you're a fab person or a back-end person, anybody running a factory, you should be very excited about this. If you're not, I apologize in advance. But it's, Inficon is my parent company. We're a Swiss company. We have about 1,250 employees. We're global. Major focus areas are in Southeast Asia, North America, Europe, and we have a pretty strong dedicated team out of a Singapore office led by Darren Lee. We are known for our smart Industry 4.0 leadership. We just heard about digital twins, etc., kind of from a global Microsoft view. We're very semi-specific. We have probably the most comprehensive operational digital twin for fabs or backends in the world. And we use that to drive a large number of applications across the spectrum of requirements and needs for factories. I really didn't bring much material on, all the various things we do. This is really more of a tutorial, I suppose, on line balance and how to deal with it and how we try to help folks deal with that. So certainly by all means, reach out to me if you want to talk about any of the other products that we provide. So the outline is, again, pretty straightforward. We're going to talk about what is line balance. We're going to talk about kind of the historical drivers of poor line balance. And by the way, when I say line balance, some people use the term linearity, like line linearity, but line balance is the same term. I want to talk a little bit about, well, how can you see something that is a very difficult concept to comprehend when you're walking around a factory with potentially hundreds, if not thousands of lots and a few 100,000 wafers moving around. We'll talk a little bit about historical approaches to improving line balance, make sure you're at least crossing those off. More importantly, and the purpose of the talk today, is to really talk about using global optimization, which is leveraging many of the things we've just heard discussed today, specifically for improving line balance within a semi-fab or factory, be that front end or back end. And then we'll talk a little bit about what does that mean and how do you see it and what are the benefits, and at the end of the day, why are we doing all of this? So what is line balance? It seems like a real obvious thing, but basically a line balance score is the average cumulative delta or difference from an idealized distribution of WIP or inventory in a factory. And so this target value for each step in the entire operation is proportional to the processing time at the step and the overall WIP in the factory. So it's not as simple as just saying I've got 1,000 steps and 10,000 wafers, so it's 100 each. It doesn't work that way. It's much more complicated. So once you have the target WIP quantity calculated, you typically include some really industrial engineering work around what's called buffer steps, etc., which deals with factory plan constraints, etc. So you've gone through this process, which unfortunately we don't have time for me to give you the full example of doing that for a factory. And when you're done, you then take this target values of what you would like to have as an ideal state, and you look at the delta from the ideal state on every step, and you take the average of that. And that becomes an average line balance. And if you were perfect, which nobody is, you would have a line balance even if you've got 600 steps of 1. That is not typical, but that is the way we measure, quantify, and track your ability to improve line performance. So line balance is often shown in multiple ways. Again, we really don't have time to go over what every one of these characters and items mean on this particular chart. In general, people think of line balance as focused on almost one of two things. In a historical, if you go back to Kanban or other short linear flow processes that are not heavily reentrant, you would look at a drum rate, which is a common exact amount of material flowing through a relatively linear line. And that's a classical, relatively easy approach from a digital twin and optimization. More typically in a complex semi-factory, which is a plethora of reentrant flows and complex tools and setups and configurations, etc. You're really looking for more of an ideal distribution of WIP, which comprehends reuse of similar tool sets, etc. And that's kind of the top view there. And again, we're not going to spend, unfortunately, we don't have enough time today to go through the exact details of how you quantify and review all the different elements. But this chart is nice in that it shows you your actual condition, obviously a lot of colors, a lot of gaps as to whether you're on track or not on track. But again, the most important thing I want to talk about today is what drives poor line balance and what can we do about it. And there's many places you can get very nice, graphical views of line balance or linearity. So N is by far the biggest impact. It is a number that no one talks about. It is the average number of like tools in a factory. So if you're 70,000 wafer a week TSMC fab and your N is 14, life is pretty good. Okay, not to say you don't have other problems, but when it comes to line linearity, that's probably the best case. And I've got a foil to show you that. But if you only have 2 tools, it's very difficult because your tools are down, because the second biggest thing that drives line linearity is extended tool downs. So effectively, if you have 2 tools and that's each tool is 50% of your capacity and one is down for a week, you are going to have a very non-linear, or what people often refer to as a large WIP or inventory bubble. So again, we'll talk a little bit about that. Some other issues that really play into this is the number of reentrant tool sets. Reentrant tool set just means a tool that is used multiple times throughout a particular manufacturing run. The classic example, of course, is lithography, where depending upon the litho tool type, it could be, if it's an EUV tool, maybe it's only 5. If it's eyeline, it could be 25. But again, those are reentrant tool sets like many other tool sets. Turns out that variability is a really big player on line balance, and I'll show you a little bit on that. It's definitely something to always be focused on. Ironically, something you rarely hear anybody talk about, but is a pretty consistent impact on factory poor line balance, is actually the planning department. I don't mean to pick on anybody working on planning today, but if you have a poor understanding of your factory's actual capabilities and you succumb to a demand from a product line or a quick desire to exceed expectations, etc., and you overcommit, typically what will happen is somebody along the management chain will decide to do something which is referred to as a local optima, and that means they're going to pull for the last couple of weeks to make some short-term goal and completely mess up your line. And I'm sure many of you on the line are chuckling because we've all been there and done that, but it's a pretty significant problem, and it's unfortunately a loop problem that gets worse over time. Operational decisions, human beings make what we refer to as local optima. We just heard about the concept of digitization of information, which is so key. But many factories still use human beings to make short-term decisions. And unfortunately, many human beings make what they believe is the right decision, but actually it turns out to be not the ideal situation and actually makes the line more non-linear. And the other thing is insufficient tool cross-qualification. And that's about the N, right? So one way to make N effectively larger is by cross-qualifying tools and allowing them to be quickly qualified for different operations. often overlooked by people, very critical if you have a factory that is not large. And then buffer inventory, we don't really have time to get into that, but either the overuse or underuse that can play a lot into linearity. So N is a big deal. We mentioned that. So in the extreme case, if you had a factory that had 1,000 starts per day, and you look at the cycle time, and you said that you had 300 wafers or so, you try to do 1,000 wafers per day. If you only had one tool in that particular flow, literally it would take you 7.3 hours. But if you actually had two tools, and I'm talking about two now for every one of the approximate 150 steps in the flow, all right? So this is a modeling output. So what's happening here is you see this exponential drop in cycle time. You literally drop cycle time by 93% when you go from a one tool line to a 4 tool of each type line. And again, that's a very, very, very important thing to understand if you're in a small to medium-sized factory, or if you're adding new technology. That's why people almost always buy two of a kind, even for a very first ramp or first new technology. This is the reason. Show it to your boss if you're not being allowed to buy a second tool. But N is by far the single biggest driver. The other big driver we talked about is cycle time. Cycle time is variability. And so process uptime variability is notoriously influential on factory performance. And so most people like to plot the CV of availability. It's just the coefficient of variation of availability. And it's a very effective way of looking at your tools. Our software and most good pieces of factory digital twins will provide you a real-time view of this at all levels. But it's important to understand that what you're trying to do is get everything up in the upper left quadrant, which basically means it's up most of the time and it's extremely consistently up. So the one that's really bad down on the lower right here is the one that is down a lot, and it's down with a very poor predictability. So it's a very random event, and it's down for days at a time, and it's down at a random occurrence level. So on the upper left is rarely down, and it's down for shorter periods of time. So obviously you would like to work with your tool set, your industrial engineering team, your equipment maintenance team, leverage all the things we just heard about to improve your overall tool performance. And it's a very, very critical component of line linearity overall. Another thing that's very important, this is starting to get into more modern factory capabilities, is real-time prioritization. So certainly a more modern factory with a good digital twin and scheduling and other advanced applications has the ability to real-time calculate its effective bottlenecks. Historically, we would think of a bottleneck as being your one litho tool. You plan the factory around a consistent bottleneck. That is not the case any longer. Almost all fabs have what's called roaming bottlenecks, which mean the physical bottleneck of the moment is varying based on the WIP condition, the down tool states, engineering, qualifications, etc. So having the ability to real-time understand the single most important tool set, and we use what's called a bottleneck score, which just means we take a look at every tool in the factory. We determine whether or not the tools up at that instant for the same tool family can meet the objectives that the scheduler has created for the next 12 hours. And we just rank that. If it's 100%, it's exactly what the scheduler needs from those tool sets. If it's 50%, that means we're going to miss 50% of the goal for the day. We better get some maintenance staff on that tool. So again, real-time tool visualization, prioritization is just become more and more critical. Candidly, it's more critical with COVID because more of the engineers are working from home. And so having the right visualization tools and dashboards is mission critical for maintaining a linear line. So now we get to the fun part, the thing that's kind of new, everything I've said so far, maybe you're thinking I know this, but the biggest thing that really differentiates kind of an average fab from the state-of-the-art fab on line linearity is global optimization, all right? So let's talk a little bit about global optimization. So global optimization is relatively new. It's really something that requires a very efficient, detailed, we like to say 95% replica digital twin. So what that means is you've got a digital twin of the factory that you're now able to drive and run scheduling and other optimization engines. So line balance is what's referred to as a global objective. And this is not a scheduling talk. I don't have time for that, but it's implied here because line balance is an input and basically a driver for each of the prioritization optimization engines that are run within a well-run, scheduled, advanced factory. And so it's very important that you've created a model and an understanding of the non-linearity such that you can then feed to the other little local optimization engines what you would like to prioritize. So if you're creating a scheduler on the global objectives, and we see litho on the left here, well, litho drives linearity. We just discussed that because it's reentrant. You need to determine and tell that scheduler which layers are more important to improve linearity. That's the way this works. So I kind of drew a little graphic here to just help you better understand that it's not just line balance. So every one of these areas, some people call them modules, usually it's a functional area of a factory, is usually optimized on its own with understanding of its nearest neighbors and the global factory. So clearly, if you're trying to manage a litho, which is a very complex module, you need to look at a tremendous number of things: APC status, tool health status, resist optimization, temperatures, hot plate temperatures, reticle management, layer, all these different things. But line balance, it turns out, becomes one of the dominant inputs in optimization for litho. It might not be as critical for an etch operation, or it depends upon the operation, or maybe a cleans operation. But again, because litho is something that's distributed across a large part of the factory, it becomes a very critical part of the overall optimization engine. Now, so you say it's important. Well, how do I figure out what I should do? And what do I feed to the optimization engine? Well, you have to do off-board analysis of the actual factory, and you have to take a look at the WIP that's distributed across the factory at every single like tool. So let's take a litho tool, and let's just say that we've got 15 steps. So I'm going to analyze the inventory at each of the 15 steps. I'm going to analyze the inventory ahead of each of the 15 steps for 2 to 3 days, and the inventory arriving at each of those steps for the next 2 to 3 days. And we're going to create a demand profile for all of those 15 layers, and then use that to drive the allocation of, think of it, allocation of the utilization of that litho tool to improve linearity. And that's happening nonstop for every single tool in the factory, of which there is more than one. And so that's the beauty of a true optimized, scheduler-driven line balancing algorithm. Now, why? Well, the main reason is that factories are not nearly as efficient as those that run them would like to believe. There are a tremendous number of hidden losses. The two big ones, quite frankly, in every factory, be it automated or manual, are standby with no WIP. That's this gray area on the left. And all that means is that a tool is up, it could run, but there's no inventory for it to run, okay? And the reason that a linear line helps is that if you have a linear distribution of inventory, the WIP is not piled up in one location, so the actual median utilization rate of an entire factory can go up anywhere between 3 and 11%, 15% would be a high case if you're pretty nonlinear. But that's a tremendous amount of free capacity. And it also, another benefit is that it reduces cycle time. Because again, cycle time is predominantly queue time in any factory with X factor. And so by having an optimized linear line, the wait time that you actually are waiting is dropped exponentially because you don't have the large bubbles of inventory, which are sitting there sometimes for days, as opposed to a linear, well-distributed line. So you gain in both better utilization of your tools and effectively, therefore, lower cycle time, which allows you to this is just another example of, it's the same chart I showed earlier, but basically, I did want to point out real quickly that there is a conflict sometimes between the drum rate and the line balance. I mentioned earlier that those are two different optimization kind of strategies. Many factories use both, but you need to manage that as to what is most appropriate for a particular area. It's part of a detailed conversation we could have at the working level. But ultimately, by putting all this information together and having a digital twin advanced scheduling system that is incorporating the line balance objectives and functions, you create literally a schedule for every single lot and every single tool and every chamber and every sequence for the next 12 to 168 hours, depending upon whether you're a front end or a back end or how complex the line is, all of which is aimed at improving the factory performance, cycle time, and line linearity. So this is a real world example of a client that we improved the linearity by 17%. That's a lot. And that correlated to about a 13% improvement in factory capacity, or about a 25% reduction in cycle time at the same capacity. So again, it's a distributed effect that has tremendous improvement. Another way of looking at this is an operating curve. An operating curve is a classic industrial engineering term, and I don't want to belittle it for anybody, but it's effectively a curve that for any given factory represents the impact of capacity on cycle time. So you see the curve, and you see the fact that it's a nonlinear curve, which anybody who's worked in a factory understands that if you load it too much, you'll get to the point where the factory's capacity or cycle time blossoms quite quickly. And that's always the challenge. Where do we run the factory at? And usually you refer to it as the knee of this curve is where you'd like to run. Some factories, memory fabs tend to run a little more to the right. Foundries tend to run a little more to the left. It's an industrial engineering thing that goes on a long time. But what's interesting is that the single best way of lowering the operating curve, which allows you to get this extra output, again, you can get either improved cycle time, or you can get improved output, or you can get both, a little bit of both, is through line balance. Line balance and as part of an advanced scheduling deployment, because they really kind of go hand in hand. And it's really free capacity or free improved on-time delivery, free cycle time improvement. I say free, I mean, it's software and there's some work involved, but it is the single largest available improvement to existing factories globally. And basically what I wanted to help you understand today is that these improvements are available, and regardless of where you are today, you should be able to improve. Thank you very much. That's my last one. Okay.
Okay. Thank you, John.
Yep. I ended up here, by the way, this is our local team is, out of Singapore, but, you can find Darren.
Okay. Good
Any
to
questions?
know. Yeah, we have two questions actually from Jay about the data that you collect from machine utilization. How do you make smart decisions from them? The downtime, preventive maintenance planning, flow sequence. For example, the decisions to be made were CapEx investment needed, maintenance planning, predictive maintenance, etc. And he followed up on whether the workflow changes over the time depends on the individual machine performance by collecting the data and analyzing it.
Oh, it's a great question. Those are digital twin questions, and boy, we could give a talk on digital twins. I think I have before. But yes, so effectively, what you have to do to create something as complicated as what we're discussing today is have a very, very precise engine, which is acquiring all of the data real time about the factory, which includes every single tool state information down to the recipe, the chamber, and you build a model of every single tool in the factory. You monitor that for change, for differences between chambers. and you use that information to feed into your predictive maintenance and other systems. So didn't really talk about that today, but yes, our general digital twin feeds multiple areas of need of a factory, and certainly maintenance, we like to call it CMMS, computerized maintenance systems, is another big area, but it's not part of the talk today. But he's absolutely right. We have extremely detailed tracking and logging and data information from every tool in the factory that is actually extremely critical for us to be able to have the high confidence in being able to predict what the future will hold. It's a great question.
Understand. So if you all have any questions for John, please feel free to type in the Q&A box. So while we are waiting for questions, John, may I ask your question? So which Fab KPI do you see the greatest improvement after you address the line balance?
Probably, I mentioned during the operating curve discussion that to a certain extent, you can choose a little bit between capacity and cycle time. I also mentioned earlier that planning often overcommits for factories. So what we see the single largest benefit is that the on-time delivery, OTD, improves dramatically. And so by improving on-time delivery, you have happier customers, you have happier planning department, and in general, the stress level of a factory drops quite significantly. And so I would say that most people start with utilizing the benefits to improve their on-time delivery as a result of reduced cycle time and of smarter decisions for critical lots and so forth. Over a longer period of time, you start seeing people looking at capacity and the next year's plan and things like that. But right up front, it's almost always on-time delivery and cycle time. It's a great question.
I see. So I have another question here. So we are talking about digitalization. So how can your software actually be better than someone who has been doing it for 20 years on the shop floor responsible for the maintenance of the line balance?
We get that question all the time, right? Well, my supervisor's been doing it for 20 years. Johnny he's perfect at it, right? So the reality is that as human beings, we just don't have the ability to see, and do the mathematical calculations. And so, even the very best supervisors we always work with, talk to, try to understand if there is some particular kernel of knowledge that should be incorporated into the decision optimization algorithm, basically take their knowledge and systematize it through the subject matter experts, similar to the previous discussion we had. But the reality is human beings just aren't physically capable of doing the analysis that's required to make these kinds of decisions, regardless of whether they think they are. I mean, it's a difficult conversation, and you have to win support by the classical supervisor, from the supervisor. Yeah.
Understand. Thank you, John. Thank you so much.
Thank you.
Thank you for the presentation and the answers to our questions. So please feel free to connect with John on the LinkedIn platform. And okay, here comes the last question. Maybe we can also address this. Is the system updating the digital twin dynamically by itself, or do optimization by its own?
Oh, that's great. It does both. So it's a learning system. It's a smart learning system. So literally it's collecting data real time, all the time. And there's a tremendous amount of analysis, real-time analysis embedded within the digital twin, whereby it's taking new information, using that to modify its model. So it's a learning model. And so it's constantly updating every single aspect of its view. And obviously it needs the most recent view to be able to predict or tell you what to do. So if you made a schedule for a factory and then a tool went down, you need to be able to immediately schedule around it, or we would call, avoid that exception. So you have to have a very, very fast system. We're typically able to reschedule an entire huge factory in 3 to 5 minutes, but the actual real-time update of the data source is in about a few seconds. But really, it's almost more limited by the client and their data stream but it's a great question, and yes, you need to have all that real-time data collection. It's a big part of our initial phase of a deployment or project? It's a good question.
Okay, here comes two more questions. Is there any value added to implement line balancing for single tool per unit step in the assembly line, which is designed for R&D customization?
Oh, okay. So yes. So I said that if you have one-of-a-kind tools, it's hard, right? I mean, I get brought into, we work with companies that are literally, we're from the US, US-based, my division. We work with the US government, small little lines, government, small volume, high mix lines. And they have an N of 1.5. And I always tell them, well, first of all, your life is always going to be miserable, okay? But we can make it less miserable, right? And the way you do that is you actually take advantage of looking at your whole factory and effectively minimizing the impact of the down events. So we can still take a factory with an N of 1, which is unique, but it would be an R&D pilot, like the gentleman is asking, and at least be able to help you, once the tool comes back up, make the right decisions for its use to make it the shortest possible time to recover. And that's what we do with smaller factories. It's a great question, by the way.
Okay, due to time constraint, I think this will be our last question.
Okay, sure.
Is the model linking up real-time to OEE?
I'm sorry, did you ask about OEE? I'm sorry.
Yeah, OEE, yeah. Is the model linking up real-time to OEE?
Yes. Yeah, I didn't have a chance to really, again, I just was kind of, I probably went too technically detailed here versus the other speakers. But we actually have a proprietary OEE model that is much more comprehensive than the semi-OEE standard, that is real-time updated all the time, and it's what we use to drive that. I mentioned earlier, we have this thing called a bottleneck score. So our ability to understand, analyze, and show you the performance of your tools is bar none, because it integrates WIP conditions with tool conditions, and also tracks all maintenance events for things like, occurrence frequencies and all that. So it's a very critical part. One derivative, when you have a good digital twin, you end up having so much knowledge about every tool that it gives you this access to really a much more, we call it ETP for enhanced tool process state. And I didn't talk about that, but by all means, just reach out to me and I can send you information on that. So thank you. It's a good question. Yeah.
Sure. Thank you, John. Thank you so much for the presentation and the answers. So for those unanswered questions, we will get back to John and get the answers posted up on the linking group.